We are joining each other after a week apart.
2 weeks. We normally join each other after a week.
Right. Okay, but it was I was very lonely. That's what I was trying to get across.
So, you have engaged what I am terming the great drive wars of the 20-teens.
Yes.
Between the EM drive camp and the warp drive camp.
See,
I'm in both camps.
Alcubierre drive.
The Alcubierre drive.
Alcubierre, yes. I was waiting for you to pronounce it so I could pronounce it correctly, and then you said warp drive, and just to try and discredit me in this battle of wits.
Yes, that was clearly a very calculated move on my part. So, Kevin, have we talked enough about the Alcubierre drive on this podcast? Have we explained what it is?
I don't think that we have.
Okay, so before we get into these drive wars, I'm going to talk about what a Alcubierre drive is, and Kevin, feel free to pitch in if you spot any inconsistencies in my explanation.
Your dad is the physicist. I will trust your...
He's actually out in the living room cooking dinner, so I can go get him if we have any technical questions. Anyway, so an Alcubierre drive was theorized in 1994. The only reason I know that is because that's my birth year. By a Mexican physicist.
And you still favor the EM drive. I can't get over you, Alex.
Okay, we will talk about the merits of the EM drive versus the warp drive or Alcubierre drive in a moment. But let's talk about what an Alcubierre drive is.
Mm-hmm.
Space, we know, is like a big trampoline.
Yep.
When you put a heavy thing like a bowling ball on a trampoline, space gets warped in. And then if you had like a marble, you could flick the marble on the trampoline, and it will orbit the bowling ball. Now, obviously, there is things called friction in the trampoline example, which would cause the marble to fall in towards the bowling ball eventually. But imagine you had a frictionless trampoline in a vacuum, and you just flick the ball.
You should be careful about that. The friction doesn't cause the force. It wouldn't cause the marble to travel in towards the bowling ball. The friction would eliminate its angular momentum.
Yes.
And the force of the quote unquote gravity of the bowling ball would eventually go. It's effectively the same thing as when you deorbit from space, right?
It'd be
the ISS is spinning around the Earth. If the ISS suddenly slowed down, then it's not moving faster than gravity's pulling it in and explosions. Not that we're recommending they engage in that procedure.
They do occasionally have to boost up the ISS.
Yes,
which can lead to some cool things.
There's a video of them boosting the ISS from inside the ISS. It is ridiculously slow and boring.
But it's still cool.
No, the ISS, it's like, you could, all of a sudden you realize you're floating backward at like half a centimeter a second. Like, well, that's interesting.
All right. That is how things in space move around, weirdly. Being in space is cool, and I wish I could go to space easily.
I want to interrupt you again, because I have a question.
Okay.
Is it just me? Or do all of the astronauts on the ISS move slower than they should?
Well, I think that's because they don't want to break anything.
It feels like they're moving their arms and stuff like through treacle. Like, is that just me? Like, you've seen this, right?
Yes. No, I agree.
It's because I can understand, like, yes, anti-gravity, there's no gravity, but that shouldn't increase the resistance of stuff. It confuses me. You know what it means, Alex?
It means I'm going to have to go to space.
No, it means they faked the ISS.
It's
actually just overcranked video. They're moving in slow-mo.
Well, we've just ruined the scientific legitimacy of this podcast. Not that we ever had it, really, but, we lost what little cred we had.
There we go. But anyway, back to your explanation of the warp drive.
Okay, so space is a giant trampoline.
Right.
And so imagine you could, bend this trampoline with your mind. So you could just think about how to bend the trampoline, and the bowling ball would just kind of move around, right? Like, you could move the bowling ball by thinking about where you wanted to move it with your mind, just by manipulating the bending of this giant space trampoline. That's what a warp drive is.
I feel like you're deliberately trying to undermine...
Kevin, would I do such a thing?
I mean, the idea is that rather than moving yourself, you are bending space-time around you. Right. There's the There's the
With your
book
mind.
that maybe you read is not with your mind, with exotic dark matter, Alex.
Oh, my bad.
Is your mind made up of exotic? Well, I suppose that's possible. Who knows? But I mean, there's the book that maybe some of us have read as a child, A Wrinkle in Time.
Very good book.
Very good book. And the idea is, there's an example that they give, and I think maybe they give this in Interstellar as well. But you hold up a piece of paper.
Yep.
And then you can walk across where the two edges, the two folds join.
Yep.
And it's effectively the principle that they're talking about with the warp drive. What differs between the warp drive and the EM drive is that the warp drive makes any sort of sense.
Wow.
In that it doesn't violate the laws of physics, where the EM drive unequivocally does.
I am not in the camp that thinks the EM drive is wrong yet. I still think it burns up information, whatever that means.
Have you learned what information is in the past 2 weeks?
So I kind of have. So I've learned that if you delete something off your hard drive heats up.
Okay.
Because...
What? No, you didn't. No, it does not.
I believe it does.
No, Alex, you're wrong.
How am I wrong?
Because deleting stuff on a hard
If you
drive
write zeros over it.
doesn't.
Like, you write zeros over your hard drive. Not you earmark it for deletion or eventual removal. You actually go in and you just write zeros over your hard drive will heat up.
Because of the electrons?
Because you've deleted information. And the information has to go somewhere.
But zeros is information. I can infer, and I can, if I have access to 99% of your hard drive and I know they're all zeros, I can guess that maybe you wiped it. If I have access to all of it, if I can look at all of the information, then I know as a person you wiped your hard drive. There's information still on the hard drive there.
Yes and no. So there's the whole concept of compressibility, right? So if you had static on your television screen, that is basically uncompressible, right? Whereas if a whole hard drive full of zeros is totally compressible, you could compress the whole of the hard drive, if it was all just zeros, to 1 0 and say, this is on the whole hard drive, right?
I'm sort of following you.
Well, because TV static, right, is just random.
Right. So if you're talking about, so you're talking about like a random distribution of off and on, if we're just talking about bits or whatever, then yes. But you would also, if you're going to try and describe a hard drive, if we were going to design an algorithm to express an empty hard drive, it couldn't just be 0. It'd have to be value 0, width and depth of, whatever sort of dimensions, and various other attributes of the information.
Yeah.
So you're talking about the bits to represent the size of the thing plus 1 bit.
Yeah.
I guess.
There was a good bit of information. I read an explanation of, what information is.
Did you destroy it?
Well, there is actually like the quantum information undeletability theorem, which states that you can't actually delete information. But I think that's...
Wow. Things are looking bleak for the EM drive, Alex. Team Warp Drive.
Ignoring that it may or may not delete information, and that hard drives may or may not actually heat up due to the deletion of information, which you may or may not actually be able to delete.
Ignoring all of the problems with the EM drive.
It's clearly much better.
You think it's viable.
So, the only problem that it doesn't have at the moment is that it still seemingly works and hasn't been disproven. That's the biggest not problem with the warp drive, not of the EM drive. It's the biggest not problem of the EM drive.
Unpack that.
That is the correct statement.
Well, I mean, I think it's interesting because there are kind of these two competing ideas for how we could ever look at not faster than light, but, well, I mean, perhaps faster than light travel, if that's...
The EM drive...
Actually, the EM drive probably isn't ever FTL.
No.
Warp drive's perfectly happy going FTL.
Absolutely.
Which is why the warp drive is much better also.
So... But I think that's also its sort of biggest flaw, right? We're not super certain things can go faster than light, and what happens when they do.
We are. Not that things can go faster than the speed of light, but that the space of the space-time continuum, the space of the universe can.
Right.
Because there are stars that are further than light has had time to travel since the Big Bang. And we know that because every year more stuff appears. And the question is, how could it have gotten out that far?
Yeah.
Because it can't travel faster than the speed of light. Space very much can.
Brought it to us.
So that part is demonstrated.
That's true.
The thing is, the warp drive does not violate physics at all. We just haven't done it because it requires a lot of power.
It requires, like, what does it require right now? A size of Jupiter, like antimass bubble the size of Jupiter to go anywhere.
I refuse to comment on that propaganda, Alex.
Whereas the EM drive can run on a microwave.
Well, there were always articles about how they changed the shape of the
toroidal,
toroidal, and then all of a sudden the energy requirements are halved and stuff. I don't know. But I think it's interesting because these are two approaches that kind of come from different from different sides. There's the theoretical and the applied, right?
Yep.
The M drive is scientists saying, this weird thing happened. We can't make it stop happening. Figure out how to make this not violate all of the rules of the universe, please.
Right. Whereas
the warp drive is us saying, this is a way that totally should work. Please do it. And NASA's like, nope, we're just going to play with this weird microwave box thing. Try and figure out why it's being weird. We're like, it's a measurement error. Please work on the warp drive. Nah, we got to work on this box.
So I will mention the experiments done by Harold White in the NASA Skunk Works laboratory. Harold White was working with something, a warp spectrometer, he called it, which had a couple of laser beams in it, and one went through a warp field that he was generating. I had air quotes that you couldn't see there, but yes, a warp field that he was generating. And another that didn't. And so far the results have been inconclusive. They have yet to find determined evidence that even on a very small scale of moving a laser beam just a little bit, they can't do it yet.
But that's because they've been splitting funding so that they can continue trying to figure out why their EM drive prototype is shaken about.
Yeah. I mean, it's even if they can prove it, it doesn't fix the energy problems required with constructing a warp drive.
The problems with energy are massive, but they're not insurmountable if you look at massive nuclear power. It's still within the realm of, like, it's entirely possible that we'll never get it to a point where we're going to have to shoot up this thing into space that, if anything goes wrong with the launch, will destroy the entire planet.
Yes.
Like, it's entirely possible that we'll go, like, we've got this thing, we've got prototypes that work, we know that we've demonstrated this, but we can't make anything remotely usable without also threatening the entire human race to do it.
The problem I see is that the warp drive, in my mind, is at least like a Type 2 civilization technology. There's this concept of types of civilizations. So you have a Type 1 civilization that can harness the entire power of its planet. And a Type 2 civilization can harness the entire power of its star. So like a solar system, and it would build something like a Dyson sphere. And then you have a Type 3 civilization, which can harness the entire power of a galaxy. In my mind, at least...
This is the Kardashev scale.
Yes, that is what it is called. Was I getting the types right?
I'm looking now. Type 1 is close to the level presently attained on Earth.
Is Type 2 a solar system?
Type 2 is radiated by its own star. Type 3 is energy in its own galaxy.
Right. So
I really dislike the idea that Type 1 is just defined as contemporary. So we will, by definition, we will never not be a Type 1 civilization.
Well, okay, it is a bit of a problem, but yes. To be a Type 2 civilization would be to be able to build like a Dyson sphere and harness the solar winds and perhaps create antimatter on large enough scales to be able to capture it and power our spaceships with it. At which point I would say the warp drive is definitely an amazing and super technologically amazing thing and is the future of human spaceflight. However, the EM drive can get us where we need to go on the same amount of power that a couple of microwaves will use. That is totally obtainable now.
Where do we need to go, Alex?
The universe, Kevin.
And even then, we calculated this. We're talking 12 years to get to our nearest neighbor. The distribution of interesting systems out there probably means that we're talking orders of magnitude longer than that.
Well, yeah,
I mean, yes, and it's not to say it would be fascinating to study Alpha Centauri and everything there.
Mm-hmm.
But as far as if we're talking about, colonization or even just communicating with other species or anything like that, we're still talking orders of magnitude more.
Theoretically, if you could scale up the power, you could get to light speed a lot quicker. Because if I remember correctly, our calculations were just a couple of microwaves. If you could put like a tokamak or one of those new German fusion reactors on board a spaceship, and really get the EM drive humming, you could probably hit light speed a lot quicker.
But you're still talking light
yes.
speed. You're still constrained by light speed.
Yes.
That's the problem. Like all these interesting stars, most of them are already dead. Not most of them. A lot of them are already dead.
Yeah.
The ones that aren't, very far away. Even light is totally behind the times.
Yeah. I mean, it's true. I will give you that on paper, if we could meet the energy requirements, I'd much rather have a warp drive, right? But I don't think a warp drive is obtainable in our lifetimes unless they have some sort of mathematical breakthrough in the energy distribution required.
I will take that as you conceding the debate to me.
I have one big problem with the warp drive, right? And that's causality. What happens if you go faster? Like, is causality maintained?
We haven't been able to test it.
Yes.
Because the EM drive propagandists won't give them the appropriate funding, Alex.
I don't really want them to test how well causality holds together, because the worst case scenario is the universe implodes and we're all dead.
Well, the thing is, you could actually do that ridiculously easily, just experimentally, right? So if you had a photosensor that turns off the laser,
mm-hmm.
and then just set up a bunch of mirrors, point, and basically then just set up the warp drive such that the light will reach it in that particular time. You could set that sort of thing up, right?
And then what? And then like a mini black hole opens and destroys the universe.
That's not how lasers work, Alex.
I was told in Back to the Future that if we created a time loop, the universe would be ripped apart. Are you really going to question Doc Brown's logic here? I think he has far more experience than you, Kevin.
As I recall, that was the theoretical interpretation. The experimental results was slowly becoming slightly more opaque.
So you're saying...
Or slightly less opaque.
So you're saying that the theory was wrong and the experimental physicists were right. Ah, okay.
The experimental physicists can't figure out why their equipment is being weird.
They're not supposed
to.
They're supposed to build us cool things, Kevin. Cool things.
Well, the experimental physicists are trying to demonstrate that this EM drive that's shaking about actually isn't shaking about. They are failing thus far. I am rooting for them to succeed and then move on to more promising endeavors such as the warp drive.
I mean, I can't believe you're criticizing light speed travel. Like, we could colonize Mars so easily. It would be great if we had like the impulse drive. The Enterprise...
Giving up faster than light travel?
I don't want to give up faster than light travel. Just wait till we have a better control over our own solar system.
But have you seen the reports about Mars? The moon is breaking up.
Which
the solar winds and the atmosphere and it's bleeding off stuff faster than... It's to the point where, yeah, even if Elon Musk got out there with nukes today... still wouldn't be able to fix the problem.
I have
Mars is toast, man.
Yes, it is, but not as much toast as Mercury. Mercury is burnt toast.
Okay, let me ask you, do you think that we will ever settle on planets in our own solar system?
I have great hope that we will settle on Mars. Most of the other ones, no. Mercury and Venus are too close to the sun. Which moon of Jupiter is it? All these words are yours except Europa. Europa. So Europa has a lot of ice and potentially liquid water underneath it. It'd be very cold, right, but it should be habitable.
There should be underlines under that very.
Yeah. Very, very cold, but potentially lots of water and rocket fuel and such. Although we might get attacked by monoliths if we land there, so it could be a toss-up.
See, I don't think we will ever... I mean, I can definitely see us making expeditions to these planets. I don't think we will ever establish permanent settlement on any foreign bodies in the solar system.
How about extrasolar
Maybe
system?
the moon. Sorry?
How about extrasolar system? So outside of our solar system. And
Well, that's the thing, is that finding worlds that are better than everything in our solar system, I think, I mean, and this is really something that I suppose would be worth looking up, but, if we were to talk, I guess, what's the sort of time span that we want to look at, and then we could go ahead and say, well, yeah, how many star systems are there within a, 1,000 light year radius, or something like that, and go, okay, well, and then throw that into the Drake equation and that sort of thing. I suspect that the availability of reasonable worlds to colonize is far too limited within a reasonable time span for us to rely on something like the EM drive, just because the speed of light just isn't fast enough to get us anywhere interesting in enough time.
so it depends on how close to the speed of light you can get and how much time dilation kicks in. If we could see that there was like a meteor coming towards us and we needed to get out of here, and we were like, well, we have this EM drive thing,
Well, then sure, you can turn on your microwave. I will yield you that.
I mean, I don't think it's not something that you're going to be able to really have a combined civilization. It'll just be a human colony that has no real contact with the original. You put
Right.
some people on a spaceship that goes fairly close to light speed. It takes them maybe a generation at their relative speed. It takes 1,000 years for people back on Earth. But when they get there, assuming it's like something even like a better Mars, because I believe on Mars, you can go outside of habitat there's enough atmosphere so you can go outside your habitat without a spacesuit for limited amounts of time, as long as you had oxygen.
No.
At the right time of day, Mars.
Nope.
Not a spacesuit. I mean, it's 1% of Earth, but I believe, or something like that.
Yeah, exactly. Yeah, 0.087 psi. The pressure, okay, from Wikipedia, atmosphere of Mars. This pressure is well below the Armstrong limit for the unprotected human body.
But what happens? What happens if you're...
You die.
How quickly?
You explode. Well, I mean, for one thing, all of the liquid boils off.
Okay, that hurts.
Yeah, so the Armstrong limit is the altitude that produces an atmospheric pressure so low that water boils at normal temperature of the human body.
Is there somewhere else in the solar system you could go without a spacesuit? I swear there was some body in the solar system that you could theoretically, as long as it was the right time of day, so it wasn't terribly hot or terribly cold.
Are you thinking Earth, maybe?
Maybe I was reading about an exoplanet, something orbiting.
Yeah, that would certainly be more likely.
The big problem with our exoplanet detection at the moment is that, for the most part, we can really only see the larger planets, because we detect them by looking at how much the star dims when the planet goes in front of it.
Right.
And you need a fairly large mass to actually detect that.
Speaking of fairly large masses, I have not lost any weight. No, but actually, speaking of large masses, Sedupiter. Is so there is news.
Okay.
News from the distant past.
Okay.
So scientists, in their infinite science-y simulation computational analysis thing, have discovered that it is very likely that there was another planet. Well, first, let me ask you, Alex, how many planets are there in our solar system?
Currently 8.
How many were there previously?
9.
But what was the ninth one?
Pluto.
No, it was Sedupiter.
Well, then there were 10.
Nope.
There was briefly also 11 then, because for a while we had something out in the Kuiper Belt that we couldn't decide whether it was
Oh,
a
yeah,
planet or
and we
not.
started adding more and more and more.
Yeah.
But they were never... Our definition... It's not that we've changed the definition, it's that we've discovered that these things don't meet the definition we already had. So they were never planets. They were incorrectly classified at the time.
I didn't
But
realize we didn't change the definition.
Sedupiter totally was a planet. The idea... So the the ideas about how the universe, not the universe, the solar system formed, obviously you have, the sun kind of coming together as clumps of gas are just like, hey, what's up? And then they light on fire. As you do when you're hanging out with your friends.
I don't know who you're hanging out with, but you might want to think about changing crowds.
Remaining balls of gas orbited around this flame, and eventually formed various clumps. One of the mysteries, to some extent, of our solar system is why there is so little debris, comparatively speaking, in especially within the realm of the asteroid belt, because Earth and Mars and Venus and Mercury are relatively small. I mean,
Yes.
the way that when planets collide with small objects, usually the small objects just fall to the planet and become part of the planet's mass. But our inner planets are so small that it really doesn't seem likely that we could have managed to kind of sweep up all of the remaining debris from the formation of the solar system. So the prevailing theory was that at some point, Jupiter, kind of dipped in to check out what all the fun was going on in that party at the center of the solar system.
And
stole all of the cool stuff. Came in, raided the thing, left nothing behind, and then us poor little blends were like, all right, we'll just chill, I guess.
I don't know. I want to interject that one of my favorite bits of solar system creation is actually how everything winds up in one plane. If you notice, when you look at a top-down view of the solar system, all the planets are all kind of orbiting coplanar.
Right.
That's really cool because how that happens is that all the objects that are orbiting the newly formed star, in our case the sun, all have their own angular momentum and are going their own way.
Mm-hmm.
But if you were to add up all those angular momentums, you'd get this plane. And when everything runs into each other, it's like summing up all their angular momentums, and they all wind up in the same plane, and it's so fantastic.
Yeah, no, it's crazy. And generally, you don't find planets that have much of an inclined orbit until you get very far out. So it's really not a matter of the distance from the star, but it's distance from other large bodies that exert a gravitational force on them.
Yeah.
Because it's the same way as Jupiter clears out so much stuff out there, keeps everything regular.
Yeah.
It's like fiber for the universe.
It keeps us from being destroyed by a giant asteroid, basically.
But so this idea, though, is that they've discovered this totally couldn't have happened now. Jupiter totally couldn't have gone in, stolen all their stuff. What they've decided now is likely is that there was another planet that was on the order of magnitude of Jupiter and Saturn, which I've decided we're calling Sedupitor.
Okay.
Look, I mean, obviously. For obvious reasons.
I think this is just an alibi that Jupiter made up, so that way it wouldn't have to take the rap for stealing all of our matter.
But the idea is that because these three planets ended up in, intersectional orbits, they eventually got flung out. And what they discovered is that Jupiter's the only planet that would have been capable of flinging it out without losing some of Jupiter's moons. Saturn, with its rings and all of its fragile stuff, Saturn's like one of those Christmas trees with the really old ornaments. You don't let your cat go near it because everything is just going to shatter.
All of it just
Right.
gone.
Exactly. This is the analogies podcast.
And the rings of Saturn, we're actually really lucky to be able to see them because they will disappear and they haven't always been there.
Oh yeah.
So we kind of got really lucky that we can see the rings of Saturn.
Well, and the rings of Saturn are actually a decent parallel for how the solar system was formed.
Yeah.
Basically, you had these rings, and then there's actually a video that I'll link in the show notes, and it's using Universe Sandbox 2. And the guy,
I love that game.
It's not even a game.
They still it on Steam.
I know, but it's not a game. It's wonderful though. But basically, you can go in, and you can be like, I put a star here and put these planets here, and then just play time forward, and I want to see what happens. But the idea is that he goes through and he creates these protoplanets. So they're, smaller than planets, and they have, this is a lot of oxygen, this is a lot of nitrogen, this is a lot of whatever. And you just put a whole cluster of them around, kind of randomly distributed around the sun. And eventually what happens is, because of their tiny gravitational interactions compared to, say, the sun, they eventually start to collide, and you end up with, over the course of millions of years, you end up with a smaller number of planets that either get ejected because of the interactions of the other planets, or they end up in stable orbits. And that's actually why we see such a planar, uniform distribution of stuff in our own solar system. And the Saturn's rings are going to do the same thing. Eventually, some of the stuff is going to, fall into the planet, but a lot of it will probably end up forming, larger objects, which will then either get flung out of Saturn's orbit or become stable, depending on how the moons of Saturn end up interacting with them.
Yeah. They could be eaten by Saturn, it could be flung off into the universe, or it could become another moon.
Yep.
I mean, those are all possibilities. Or Jupiter could come along and steal it.
Jupiter's kind of like the bouncer of the universe. Like, ejecting... He's the bouncer that killed the other bouncer. Like, that's the...
Wow.
Poor Jupiter got flung off into space and abandoned.
Where is it? Can we predict where it might be?
That would be fascinating. I didn't see anything like that, but that'd be really cool. Can we chase after it with the EM drive?
Well, not the EM drive, I doubt, but that would be a use case for the warp drive. We'll go out and we'll get it and bring it back.
There we go.
Just warp the whole Jupiter back into orbit.
That would be brilliant. Well, I suspect that there's no way to put it stably.
Just put it in Pluto's orbit. I
mean,
you could do it.
You could put it in... Yes. You would have to also move Saturn.
Well, I mean, if we're going to go retrieve this giant planet, I bet we could do it.
Right, exactly. So this is no big deal. You could put Saturn and Jupiter in the two stable Lagrange points. Because those are reciprocal Lagrange points. So Jupiter would be in Saturn's Lagrange 3, Saturn would be in Jupiter's Lagrange 3, or Lagrange 4.
Right.
So, so basically they're 3 spaced out. Actually, that is really cool. That is really, really awesome. So the Lagrange points are basically points that are very weird in space.
Yes.
So
they're awesome.
Right, they're fantastic, and they're great places to put space stations. Don't know why we're orbiting. Seems kind of dumb. But basically, the idea is that your angular momentum dictates the radius from the body that you're orbiting.
Right.
So if we go faster, we're boosting ourselves up into a higher orbit. The interesting thing about Lagrange points is that they're particular points in space where the interaction with another body manages to pull you along faster or slower than you should be moving based on your radius.
Yes.
Like the Earth has a Lagrange point that is closer to the Earth than the Sun. Now, if we imagine Mercury, it spins around the Sun much faster than we do.
Yeah, I don't remember how long a Mercury in year is, but not very long.
Right. So, if we bring it down into a lower orbit, if we put a satellite out there, it should orbit the Sun faster than us. But instead, it ends up staying at the same speed as us because we're exerting an opposing force, because the Earth is exerting an opposing gravitational force that is the right amount to cancel out that additional amount.
Yep.
And so there are a couple of these points. One is on the opposite side of our orbit.
Yeah. There's one on... There's a moon... There's moon Lagrange points as well, so you can go like in between the Earth and the moon on the far side of the moon.
Yep. So there's the far side, there's the near side, and then there's to the left and right.
Right.
And there's a fifth one.
Oh, correct.
I don't remember. Oh, no. The fifth one is on the opposite side of the orbit.
Yeah.
So exactly opposite the moon. Whereas, because now the moon and the Earth are pulling on you with the same force, but from the opposite side.
Right.
Only 2 of them are really stable. That is, it's very easy to fall out of being on the far side and the near side of the moon or on the opposite side of the Earth. Mm-hmm. The 2 to the left and right tend to be relatively stable, that even if you get jostled around, you'll eventually kind of circle back into that spot.
We're about to put the James Webb Space Telescope out on the far side of the moon, though, I believe. I believe it's going to be its orbit, which... And the James Webb Space Telescope, I believe that's the name. That's the right one. There's a whole bunch of different space telescopes. The James Webb is what we're going to be using to find exoplanets with far greater precision than we have been before. We used to have Kepler. And I think Kepler might have also been out there. I don't remember where Kepler was orbiting. Maybe that was the one that was in the far side Lagrange point, but I don't think it was. And Kepler broke down, unfortunately, before it could really be used to find everything we wanted to. I think it completed its primary mission, but it ended very quickly after. The James Webb Space Telescope might eventually, not by itself, but perhaps we could build many James Webb Space Telescopes and use them as, like, the very large telescope in space to reveal, like, exoplanets.
The very large telescope. That's still my favorite telescope.
Yes. But now we could put it in space, and we could reveal exoplanets down to, like, not super high detail, but, you know, maybe we could resolve, like, 10 by 10 pixels of detail.
Right.
Which would be awesome.
And the far side of the moon is a great place because you're not dealing with the reflection off the Earth and that sort of thing.
Yeah.
It's not a stable Lagrange point, which basically doesn't really mean a ton. It just means that you have to occasionally perform corrections. If you put things in Lagrange point 3, so putting satellites out there is perfectly fine. Putting a planet out there, not fine.
I think if we've moved the planet in from, like, way out on the other side of the solar system, we can probably do orbital corrections.
But that's the thing. We could put if we put Jupiter and Saturn in Jupiter's 3 and 4 Lagrange points to the left and the right of Jupiter in the same orbit, then Jupiter would be in their Lagrange points. And so you can that's really cool though. You can have 3 planets in the exact same orbit, spaced out by 60 degrees.
Yes.
That's insanely awesome.
I mean, you'd probably have to balance it out because of mass, like, because obviously a satellite doesn't really pull on the moon that much, whereas Jupiter would pull on Saturn a ton.
Well, it doesn't. You just have to make sure that the angular momentum is correct.
Yeah.
So as long as the momentums are correct, well, I mean, you could do that by changing the mass as well.
Yeah. So
that is really. We should do that with Earth. We should just create 2 other Earths to the left and right of us in the same orbit. Like, if you think about it, if we were going to colonize a system, that'd be like the coolest way to structure stuff. It'd be relatively trivial. You just boost your orbit up for a little bit and then bring it back down. You'd transfer between those planets. It feels like it'd be a lot easier to transit between those than transiting to, say, like, Mars.
I mean,
like, if you were going to design a solar system to live in,
yes,
I'd totally just have an orbit of 3 habitable planets in the same orbit.
I mean, it's unfortunate that, you know, the universe doesn't work that way when it's, like, building itself out of random dust.
I know, it's really obnoxious.
I'm just happy that it's here at all.
I'm still ticked off about Jupiter, man.
We'll go find it, Kevin.
We better. Poor Jupiter just got flung out and is abandoned. We don't know. I mean, it could be that it's in some crazy trajectory. Could be floating out to Alpha Centauri. Maybe it's going to take revenge on some other poor, unsuspecting system. You never know. It'll sweep down, steal all of their stuff, fling it out into space.
I mean, if it came sentient and was like, oh, it brought me back, I can plot my revenge now, and then it just flies around and knocks everything out of...
There's an idea for a story. I gotta write that. The Revenge of Jupiter.
The Revenge of Jupiter. So you have been writing a story. Is this what your story you were writing about was?
No, it had nothing to do with Jupiter. No, I wrote a novel for National Novel Writing Month, and I'm done.
Is it good?
Yay. No. Oh, it is. It is really not good.
Oh, okay. Well, is it clay you can mold into something good?
Probably not even that.
Are you going to let me read it?
No. No, it's the idea with the National Novel Writing Month is that you write a novel that needs to be 50,000 words in the month of November.
Yep.
Which works out to writing about 1,600 words a day. I managed to wrap it up a little early, and yeah, I'm not a fan of how the story turned out. But it was space-abouty. What is that even?
Space abouty.
No, it was. I mean, it was set in space. So you may have noticed that Star Wars, Star Trek, Battlestar Galactica, pretty much every sci-fi series, all sort of pretend that there's gravity where there isn't.
Like on a spaceship?
Yes.
Well, that's
just for example.
That's anti-grav in reverse plating.
Right. So the thing about that, there's not because I was trying to look at for this novel that I wrote is that I wanted to have a slower than light travel between systems.
Yeah.
So I wanted this big ship, and I wanted it to be not unrealistic, but not necessarily tied to being fully scientific enough
Right.
that you pseudoscience-y enough. And I read recently Ray Bradbury's The Martian Chronicles. I don't know if you've had a chance to read it.
No, I haven't.
It's interesting because it was in the 50s or 60s. But it talks about like landing and finding Martians and breathing the atmosphere and plenty of things, and tries to present this as like a near future Earth type of fiction.
Yep.
Now, granted, it's fiction. There's no expectation of being scientifically accurate. You're entirely entitled to do whatever the heck you want. But what I've noticed is that in books, you have kind of two options when you're dealing with world building. You can either say that this is the current world you know, and I'm going to enumerate the exceptions to you.
Mm-hmm.
Or you can say, I've got to add an additional 30,000 words to this novel so that I can explain the universe and the magic system and the, whatever the heck it is. No, I mean, really, that's what it is.
Yeah,
Is that
no.
The benefit that you gain for not postulating some alternate universe that you have to then describe the rules to, is that the reader has a reasonable expectation of going like, okay, so I'm going to assume that this is taking place in the real world until you tell me that, with these few exceptions.
Yeah.
So, I could say this is New York, but after an apocalypse. You still assume people know what the word radio means. You still assume, you can make all of those assumptions. If you postulated an alien world, the reader doesn't get to assume that they've even heard of what a radio is.
Yeah, or you could just say, this is New York, except it has a TARDIS. And then, just time travel.
But then you're still basically signaling to the reader that these are the assumptions that you're allowed to make about the universe.
Yeah, I get that.
That you're reading the story in. So the thing that struck me about the Martian Chronicles is that this was in the 50s and 60s, and it was postulating like totally an atmosphere on Mars, totally possibility of Martians, and it was presented as like the nuclear arms race comes to a head on the Earth and things like that, and so it's presented as this sort of near future, real-ish world scenario with and maybe there might be aliens, which to me communicates the idea that at the time, the popular conception was maybe there could be aliens on Mars in the 50s and 60s, which feels weird to me.
Well, I believe at the time they'd still were postulating what the canales were. So on the surface of Mars, there are these trenches that when they were originally viewed through telescopes, I think in the late 1800s, an astronomer termed them canals, or whatever the French or Italian word for canal was, just whatever background he was, because he assumed, oh, look, there's obviously some form of life on this planet that has built these great canals into the surface of Mars. I don't know when they figured out that wasn't the case. Do you remember what year that book was written?
So I ended up actually going to Reddit Ask Historians, which is /r/Ask Historians. I was like, when did we give up on the idea of life on Mars? Basically, yes, there was still the possibility that there was a subterranean Martian population at the time.
Okay.
Based on our best understanding, the idea that there was an atmosphere or much of one was pretty well nixed by 1900.
Okay.
1900 to 1920, somewhere around there. Of course, dissemination of scientific information was not the same then.
Yeah, absolutely.
So in terms of popular consciousness, who knows? The War of the Worlds, same deal. I think that was 1930.
That's a very good point, because people actually believed that, and so there must have been some sort of...
And it's been obviously hyped up a little bit.
Yeah, I'm sure.
Looking back, like there were fewer people that were in a panic than perhaps was reported. But still, I mean, the idea that you could even take it as a working hypothesis seems a bit weird. That basically, if I were to write a story now where we landed on Mars, walked out without spacesuits, and said, "Hey, how's it going?" It'd be very difficult for anybody to read the story and not just throw down the book. Unless I said, like, back in, 7 billion BC, or in some strange Earth-like separate universe. So, you have to make up some sort of fake explanation for how this thing can exist. Much like in Harry Potter, right? J.K. Rowling had to roll over backward to come up with explanations as to how this how the fantastical parts of her story could fit in with the real world.
Yep.
Whereas, like, if she decided to set it in Narnia, you don't have to do that, right? You're postulating this fake world, so the audience goes, "Okay, fine."
Yep.
So, like, it's basically that whole thing. So I was trying to write the story, and I discovered there's no pseudoscientific way to have decent gravity on a ship.
You rotate the
There's
ship.
really no way to make it happen.
You spin the ship.
Yeah, but even then, it's like it's iffy. Because you're still dealing with issues of different gravity based on what part of your body is. So you'd have to have something ridiculously enormous to the point of being impractical. You'd have to give it an enormous amount of power.
Yep.
To account for everything and keep the rotation constant. And then you still have the problem of how do you actually get out of this rotating thing?
Well, you just open the hatch on the floor and fly out.
Well, I mean, how do you get from that to the main core? If you have some sort of sphere that's rotating around the body of the ship, getting from one to the other is challenging.
Yep.
Setting up gravity is really, really, really hard. And in particular, this one that I was trying to write, I wanted to kind of explore this idea of, like, this very big transport ship. Like, if you're talking about, I mean, there was even the idea of actually putting up a small rotational proof of concept on the ISS.
Yeah, they did.
That's doable. It's the sort of thing where they weren't going to keep it powered all the time.
No, absolutely not.
Because it's way too expensive. But something of that size is somewhat feasible. If you're talking about something, if you're talking about a ship with a crew complement of like several hundred or more.
Yeah, unless you can find some sort of, like, super dense material that you could turn on and off its density.
Right.
Then, I'm not sure. I'm not sure what the pseudoscience behind even the Star Trek one was. I remember in Enterprise, they did have rotating ships for a while. They'd have events on, like, older cargo ships that had been apparently running around at sub-light speeds for a while. And those had rotating parts and pieces, but obviously once warp drive in terms of, like, the Enterprises came along, they were flat, didn't spin, and had gravity.
I seem to recall at some point, and I don't know where I heard this. This is back from when I was a kid and was trying to say, like, where's the gravity when I was watching Star Trek. And someone explained to me that at least their understanding of the pseudoscience explanation was that underneath the floor paneling was a disk that rotated, and somehow there was some idea that would generate.
Okay, now,
yeah.
I mean, if you spun it at, like, near light speeds, relativistic mass would kick in, and it would gain mass. If you were spinning this light at, like, this disk at, like, 0.8 C or something.
So there you go. That would actually do it, right?
That would.
So it gains mass, and thus it draws the stuff above it down toward the plate, and you've just got this flat thing on top of the disk. So maybe that was the actual explanation that was used in the Star Trek blueprint manual thing.
The reason I know this is because I remember in Deep Space Nine, which you haven't seen. This isn't a spoiler. They had A, variable gravity in different parts of the station, and B, at one point they built a light sail ship, and that had grav plating.
Okay.
So there is something they call gravity plating, which has a Memory Alpha wiki page that basically says it generates gravity. So,
There's one sort of technique that was a little bit promising, and it was based, and it's something that they've actually demonstrated. They've been able to levitate a mouse with it. But the idea is that they send out compression waves such that they intersect at the right point.
So what type of compression waves? Sound compression waves?
I think it's sound compression waves. So that basically the air just happens to compress at the right speed at a particular point where the waves meet. Like you do with radiation therapy, right? Like pointing one radiation beam at someone will just burn their face off. Pointing two half-powered radiation will burn off the point where they intersect, but not the point where only one of them hits.
Right.
So it's the same kind of principle that you're just firing these waves, and it generates enough motion at the point to kind of keep the thing stable. But the problem, though, is that works at one particular fixed location.
So your big toe.
You could even sort of spread out. Right, so like you could stand in a room and nobody else could.
Yeah.
Even if you expanded it out, there's really no way to set it up such that you can be like, oh, yep, the ship's totally gravitied now.
I think the relativistic disk is going to be your best anti-grav thing. Well, it's really real grav? It's not anti-grav, it's just gravity. It's your best artificial gravity. That's the right phrase.
I mean, the problem with that is if it's a mass large enough to exert that sort of gravity. Well, no.
It'll be a very thin disk. It just has to spin very fast.
Right. No. But I was just thinking if you get it up to exerting that amount of No, I was just thinking, well, then its apparent mass has got to be so huge that it collapses the ship. But no, it would just pull on the ship at the rate of, I don't know, gravity.
Yeah. I mean, and on the hull of the ship, I would imagine, because the radius is going to be so variable, that it would drop off quite quickly. So, like, if you were on the outside of the ship, you'd feel less pull than on the inside of the ship.
Well, it should be exactly the same as like what I feel on the 15th floor of the building.
Oh, maybe
you're basically just creating the floor of the Earth underneath your ship.
Well, okay, so I mean the equation is GMM over R squared, but that's for an Earth's gravitational constant, right? Does that have anything?
Right, I don't know how you're going from it spinning to it generates gravity. I'm just assuming that you're creating an object that is able to produce enough gravitational force to be equivalent to gravity. The gravitational constant, by the way, has nothing to do
with the radius?
No, the gravitational constant has absolutely nothing to do with the amount of gravity that Earth has.
Okay.
It is just a conversion measurement.
Okay.
And it happens to be the same. And it happens to be 9.8, which is really freaking confusing.
Yeah. Okay.
But it's just a constant that's a unit conversion.
Okay. I couldn't quite remember how that particular thing worked. No, but the disk would not like have any inherent mass to it. It would have a very small amount of mass, but you'd have a Lorentz transformation upon its mass as it's on the outer edges. So actually the outer edges of the disk would have more mass to them than the inner edge because they're going to be spinning faster.
What happens then?
I don't know. You might, I don't know.
Well, they've got to be spinning, and they'd have to be spinning at such a rate.
You might
that gets into the same problem of...
You might have to have a tapered disk. So if you had like thicker in the middle and thinner at the outside, so that way the Lorentz transformation as it went out would be constant. So you could actually wind up with a constant gravitational pull across the whole disk.
The problem is that with even things like carbon nanotubes, the problem is transferring that momentum to the outside of the disk.
Yeah, it would rip itself apart.
That the propagation would not happen fast enough to get up to that speed.
It's just transparent aluminum. It's fine.
All right, but yeah, okay, so if we postulate some super strong material...
Yeah.
Then yeah, we could... Then, okay. But then, so yeah, its apparent mass then just effectively puts, the planet beneath the floorboards of the ship. Okay, that's brilliant. Now I'm really mad, because I spent this entire novel, and I kind of realized this. One, if you're making a movie... It's really hard to just be like, we're going to have a crew of like 1,000 and there's no gravity.
Really big vomit comet.
But also just, it's really hard to write. Because every time, like I sat there like, and they pushed back, and then they flipped up and then saw this reference frame and like, you're just constantly having to reorient the reader.
Yeah.
in the story that you're describing. And I sit there, it's like, okay, I guess I understand why everyone goes, I can't figure out how to fake science this, but I'm doing it anyway. Because there are a lot of, because, Star Trek in particular tries to be very good about its pseudoscience.
Yeah, it does.
It tries to, and granted, limited by its understanding of science at the time that the stuff was written, but it tries to at least postulate, like, here is our guess as to how this could be. Like, obviously we come at this from the point of we want to tell a story that needs these particular devices, and we're going to try and retcon those as best we can. And we're not going to go, well, we can't figure out how to make this happen, so it's just not going to be a part of the story. But, they do the best that they can to try and come up with a reasonable, grav plating aside.
Yes. Gravity plating clearly just works by itself.
Okay, now I'm super excited about this relativistic disk idea.
I wonder if it was, clearly someone thought of it because you actually told it to me, but
I haven't, well, this is back, back when I was a little kid. And I was just curious about stuff. I have no idea where that came from. See, that was the thing before the internet. There were no sources of information. There was no such thing as a primary source.
Yeah. I wonder, spinning disk, artificial gravity. See if
I think that's just going to give you the toroidal.
Rotating wheel space station.
Yeah.
Artificial... Yeah. I don't know. No one will know where... Maybe that was like one of those... That's the Beethoven paradox all over again. Someone traveled back in time, told it to you, so that way you could tell it to me, so I could invent it, and then...
There we go. We're going to be rich, Alex.
with our impossible rotating disk gravity.
See, the thing though is that you could actually do that on... You could do that on the planet for just, like, weight training easy. Like, easy forms of weight. Like, instead of just you'd have a gym where the floor underneath all the treadmills, you just have a spinning disc that ups the gravity to 1.5 G or something.
So easy being relative to the fact that we need to spin an object at the speed of light. Or...
No. I mean, easy as far as like physical labor. Like, because the problem with weight training and things like that is that things are not uniformly distributed. Like, the big damage that comes from doing lots of forms of exercise is the possibility that things will become distributed wrong and you'll tear something.
Yeah.
If you're just like, we're just going to turn up the gravity, that's a much better way to exercise.
Yeah.
Because you're guaranteed that everything's going to be distributed.
Yeah. I mean, it would be super cool, but very energy costly.
Meh.
I mean, actually, you might even... Ooh, here's something interesting. So, Einstein equivalates mass energy to one another, right? So, and electrons and such are massless particles in photons, but they're still attracted to black holes because they have energy. So if you just pumped a lot of energy into a piece of metal, it would therefore increase its mass energy equivalence and it would attract greater. So you just need to put enough electricity through a plate. If you put enough, maybe that's how it works.
Are you equivocating electromagnetism and gravitational force? Did you just connect those two things? Did you just make them the same thing?
Kind of, yeah.
Alex, I think you may have come up with the theory of everything that people have been trying to get at for a very long time.
I mean, photons are massless, yet they get attracted to black holes. So use whatever process by that works to build to build this electromagnetic plating that has a gravitational pull on it. There.
I mean, if there was a way to... I mean, it's also possible that you could look at things like... I mean, this was another kind of theory of for pseudo-antigrav is just setting up magnets.
Yeah, but that doesn't make any sense.
Like the iron in your... What's that?
Oh, okay, the iron in your...
Yeah, the iron in your blood, basically.
I mean, they levitated a frog that way.
Yeah, but it feels like that'd be really uncomfortable. Also, and eventually, your brain wouldn't get any iron.
Also, how would any of your computers work?
The computers tend to be resistant to magnets now, right?
Yes.
Because now we're not using tape discs anymore.
I suppose, but in order to generate that sort of field, you'd need an electromagnet, and that's not just going to be magnetic waves, that's going to be like
That's. I mean, you remember Breaking Bad? They got the enormous magnet, and that didn't pull their iron out.
No, but it did.
That didn't even manage to pick up a person. So yeah, we'd have to go orders of magnitude more than that. So okay, yeah, that's also not particularly feasible. But some way of generating gravity based on throwing in a bunch of electricity is a much, much, much better way than let's try and get something spinning at a ridiculous speed.
Yeah, but
it's just much more feasible from a can we ever imagine being able to do this sort of perspective.
So I would almost wager that that's perhaps the theory they're working under is the mass energy equivalence. So they figure that, well, in the future, we'll have a theory of everything that unites electromagnetism and gravity, and we'll be able to calculate, how much electricity we have to pass through this plate to generate what sort of gravitational pull. And I bet that's how the grav plating in Star Trek works. But
it's an inert material. It's not like we got to plug in the grav plating.
But the grav plating systems can fail. I've seen them fail.
Oh, okay.
I think that was another thing in Deep Space Nine.
Okay.
I think, or maybe it was Voyager. I don't know. I swear I've seen them fail. But yeah, the amount of electricity
they just ended up with like overflow special effects budget, and they're like, let's nuke the gravs.
Actually, here's what you do: you get a superconductor. If you had a room temperature superconductor, you just pipe that much energy into it, and it's just a big capacitor. It holds all that energy in the plate, right? And so you now have this plate that is a superconductor, so it has no resistance, and it just has all this energy in it. And the mass energy convergence says that it has mass, and therefore will attract you to it.
So, Alex, since you brought up the point of EM drives,
yes,
just is your obsession. Tardigrades.
Yes.
Tardigrades are super awesome. I don't think we have talked about anything that is not space related.
Well, I mean, today everything is space related. It's all in space.
That is true. So there's an article that came out studying tardigrades, nature's most awesome animal.
Yeah.
That indicates that they have more foreign DNA than anything else.
Which clearly means they came from Mars.
Well, so that is the point that I should clarify. When they say foreign DNA, so that's the thing. Scientists use words as though those words aren't used by normal people, and they can just use their own definitions.
Yeah, and?
It's like, you should use, if a word has a particular context, you should just stop, you should use a different word for your scientific term. Just stop using for any. So when they're talking about foreign DNA, they're talking about DNA that is still earthbound, but has no business being in a tardigrade. It'd be like finding out that humans have lobster eyes. I mean, it's the idea that they have DNA that is from species for whom they could not have crossbred and are like completely foreign, being the word, to their particular way of life. The interpretation of this is that because tardigrades are superhuman beings that live forever.
Yeah.
They don't live forever. But because what happens is when they are, when their lives are threatened, they basically exude all of their water and they become 4% water by body mass.
Yeah.
Which is insanely low.
We're something like 70 or 80 in that range, right?
Yeah, something around there. And they are too when they're alive.
Yeah. But
when they go into hibernation. Yeah. And this is the way that they survive, is because the problem with being water is that when temperatures get really low and the water becomes ice, the ice is larger and will pierce your entire body.
Yeah. Why your ice cream doesn't taste as good if it's like water and then
exploding you.
Frozen. Yeah, well, that's true. That too.
Exactly. I've never enjoyed ice cream while it's exploding me.
Can't say that I have either.
But so the theory is that because they spend so much time like this, the chromosomes in their own DNA are much more inclined to fracture. And during that time, the DNA of other things like small, tiny bacteria will sometimes just get fused when they recover.
That's amazing.
Just be like, oh no, we're missing the what should I eat for breakfast gene. Oh look, here's one. from this other thing. Let's just use that.
I wonder what my what should I eat for breakfast gene is. It's probably nothing.
It's bacon.
No,
it should be bacon.
I don't usually eat breakfast.
If it's not bacon, it's a recessive gene, Alex.
I should eat breakfast more. That's the lesson of this story.
But I think this is freaking awesome. And insane.
And weird.
Right, because when our genes get messed up, we get
die.
cancer and die.
We just die.
We get cancer first, usually.
Sometimes
unless they get
just
really,
die.
really messed up. Basically, this is not only like not only do the tardigrades genes get messed up, they're just like something else has probably got some of this figured out, and they just steal. It is just insane.
The fact that they can figure out what other genes do in other things and then incorporate them into themselves is a really weird theory.
Well, and they may. I mean, I don't know if that's necessary. I don't know if it's necessarily that they're like pulling out a particular. It could just be that the genes get spliced regardless of.
Oh, just at random.
Of the phenotype, right? Yeah. They just get kind of at random, and just because they're such a prolific species, sometimes it works. But they have, a much higher, a ridiculously high amount of foreign DNA in their systems than other species, which is just so. Not only are tardigrades invincible, they didn't even figure it out themselves. They're like mutants. They're Frankenstein monsters.
They're the Borg. They are the Borg.
It's insane.
Just absorb everything around them, and
but that's the thing is, how do you do that? You absorb everything around you indiscriminately. And you can survive everything.
I don't.
How does that work?
Well, I mean, obviously, whatever original cell they were using to get the DNA from didn't survive. They didn't just like remotely scan them. So on a cellular level, it's not that discreet. But I don't know.
I mean, I suppose in some ways, maybe this is a more advanced form of sexual reproduction.
Yeah.
In that, because back when species weren't super into that, they would reproduce by simply cloning themselves. And then the only opportunity for advancement, you weren't going to get promoted just cloning yourself. The only opportunity for advancement was for something to go wrong while you were cloning yourself. Yeah. You end up with a defective clone that happens to be good at math, or whatever their benefit is.
Or twice your size, yet still, like, physically viable.
But probably just better at math.
Okay. Yeah, that we got math at the single-cell level. That's right. how good at math we are. We figured that out long.
Yeah. And then, of course, sexual reproduction has more benefits because you're improving the diversity because you're basically taking two completely different DNA strands, and then you're just picking and choosing random ones. And so you end up with people that are much less like their parents.
Yeah.
But when you have a lot of kids, then there's a lot more opportunity for diversification.
Yep.
And, there's still the mutation component, which is great. But it also maybe sort of explains why we spent such a long time as single-celled organisms.
We spent it took like 1 billion years.
Right, and that's the idea of sexual reproduction is perhaps what has shot us out into crazy evolutionary territory.
Yeah.
So I'm wondering now if maybe the ability to just be like, whenever, just go, to heck with this gene. Let's just like grab something from somewhere else. That basically is just a way to encourage mutation all the time at random, and probably most of the tardigrades totally die.
Okay.
Like they're like, hey, let's take an E. coli chromosome and see how that works.
Oops.
Nope. Right? But because they're doing this on such a regular basis, that it's actually allowed them to evolve much faster than even sexual reproduction has been able to do. Yeah. That's my theory, maybe?
So my theory is that they are Kirby. They're the predecessors to Kirby. And eventually tardigrades will just turn into Kirbys, and we'll have a race of Kirbys running around.
Tardigrades are awesome.
Yeah, that's a very cool theory.
It is they are such a cool species. I would like to combine tardigrades and what is it? Is it jellyfish that live forever?
Yeah, there's a species of jellyfish that can basically turn back its life. It can revert back to like a very small organism and then regrow.
Right. So the idea is that basically you go from stem cells to not stem cells to stem cells to not stem cells.
Yeah.
Which is something that I believe we've been able to do with humans. We've been able to take adult non-stem cells and stemify them in very limited circumstances and situations.
Yeah. Because stem cells they're crazy because they can be like any cell. So we have like obviously you have a heart cell. Well, not one just heart cell. You have a whole bunch of heart cells which build up your heart. You have a bunch of brain cells that build up your brain. Stem cells can be told which cell to become. They can be like, you are now a heart cell. You are now a brain cell. You are now a skin cell.
Right.
Which is what makes them so crazy cool.
Right. But theoretically, every gene or every cell has the full set of chromosomes.
Right.
So they have the information. The information has not been destroyed, Alex. That's why they're super cold.
So snakes have all of
Snakes have so much information, man. They know all the things.
That's why Slytherin was a very good house.
There you go.
So wise was because...
I think your theory of everything is starting to fall apart, Alex.
My theory of everything has nothing to do with this. It has to do with electromagnetic plates and why photons fall into black holes.
I forgot what I was talking about.
You're going to combine tardigrades and so you just stick a whole bunch of tardigrades on top of a jellyfish, and they'll consume the jellyfish, absorb its DNA, and then become a super mutant and destroy us all. Good job, Kevin.
Honestly, I feel like tardigrades are better equipped to outlast us than we are the reverse. If that makes sense.
I mean, yeah. I mean, they're not susceptible to the Great Filter like we are.
Right. Tardigrades are... Because they found tardigrades in the Himalayas, in the Mariana Trench.
In space?
In space.
They didn't find them. They put them there and then
But they found them again.
Yes.
They live freaking everywhere. They can be exposed to insane amounts of radiation, insane amounts of pressure. Because they're just like, fine, I'm just not going to be a water being anymore. And I'll wake up when it's done.
Yeah.
And that seems like a brilliant strategy for life, right? When things aren't going your way, just go to sleep until things get better.
Just copy your brain into a whole bunch of tardigrades and then, in the future reassemble.
Well, I mean, they are actual animals. They're not just bacteria or anything. They're just microscopic animals. They have brains, they have guts. They're just, incredibly tiny.
They're very tiny bears.
Yes.
They
totally don't look like bears at all. I don't know why that nickname.
They're called water bears.
Yeah.
They look like bears, I think. They look like bears. They have a face. They have a weird face with like a snout. And,
sorta.
12 legs like the bear's back.
Right, like bears do.
Yeah.
Maybe it's the hibernation, actually.
It probably is the hibernation.
That's probably it. It's the hibernation.
Probably.
But man, can you imagine though, because the tardigrade, I believe their lifespan is something like 10 years just on average. And it's just when they go into that hibernatory state. It's not, I mean, that'd actually be kind of smart if they just figure out, like, if you're about to die, just hibernate. And it's, effectively the same as like the cryo freezing that we do, but a lot cheaper.
And works.
We just got to convince the tardigrades to go into hibernation until we could figure out how to get their stem cells going.
We're just gonna fuse people with tardigrades. That
oh man,
sounds like
that'd be
nothing
really
could
awesome.
possibly go wrong. Nothing could possibly go wrong.